Hi, I'm Derek Alawa, and today I'm going to be talking about predicting laser polished surface characteristics with machine learning. As you can see from these first two figures, I'm able to do this very successfully for the characteristic of depth and somewhat successfully for the characteristic of roughness. An ultrafast laser is used to write lines in glass surfaces. These lines can be thin and measured as depth only, in which case we're able to predict the average line depth with a very small prediction interval, or they can be wide, in which case I treat the bottom surface of the line as a separate surface from the main material. Each of those surfaces, the surface material and the line bottom, has a depth and a roughness. A feed-forward neural network is able to predict the average surface roughness of that line bottom with a somewhat small prediction interval. Improvements that can be made on this process are using larger data sets, especially for wide lines, comparing entire surfaces before and after polishing rather than using only after polishing data, and exploring image-based deep learning methods to potentially increase accuracy. Surface modeling is performed to improve the laser polishing process. It's a complex process with multiple input variables and a dependence on the material used, and the ability to better predict the outcome of this process helps reduce preliminary testing and failures and the waste and expense that those incur. Machine learning contains a versatile set of methods for prediction and modeling, some of which have been used in conjunction with laser polishing in the past. And what I'm doing here is, given a set of laser inputs and some data about the surface before polishing, I can model the output surface characteristics of the polished area, be that depth or roughness. An ultrafast laser polishes a line in a glass surface. It does this with a set of input variables. There's laser fluence, scanning speed, pulse repetition rate, and the number of passes over the surface. The output is a written line in the surface, which we can measure with a depth map. The prediction uses data from the laser inputs and the unpolished surface to model the expected output of the polished surface. A neural network is used to programmatically develop a model. We have a set of inputs and then a known output. In this case, for a thin line, that output is the measured line depth. That set of inputs is sent into the model. And across multiple data points, that data is segmented into training and testing. You can have a set of training vectors and a set of testing vectors. The method of testing that I use, leave one out cross-validation, trains on all of the data points available except for one, which is then used to test it. The training function updates the network settings to optimize the model and give the best performance possible for the set of training data. And then performance is quantified on the test data point. The inputs are sent through it, and then the output is checked against the known output, and then that is used to quantify the performance of the model. You can then cycle out the test data point across all of the different data points that are originally in training. In this example here, that'll be A through K. And then that's used to get a large set of performance predictions for the model. So the machine learning method here used is a feed-forward neural network. Using this example, we have our vector input. And use all of the inputs for a wide line in this example, which is the 4 inputs from the laser, and then 2 from the surface, which is the initial roughness, and then measuring the thin line depth. These are sent in to the system as a vector. That vector is sent into each of the nodes in a hidden layer. And these nodes all process that vector and give a vector output. Those outputs are then summed, and then that new vector output is sent into the nodes of a second hidden layer. And this can go on for as many hidden layers and as many nodes as desired. At the end, there is a single output layer. There can be multiple, but in my case, I have only a single output. And that is processed one more time, and then that output vector is summed into a predicted value. In this case, predicted roughness, the line bottom. Inside each of those nodes is where the processing happens. And you can see in the diagram that I've drawn here what happens. The vector goes in, and each element of the vector is multiplied by its own weight. This weight is initially randomized, and that is independent for each different data point within the vector. Each of those results is then added to a bias value, which is the same for each element of the vector. And then each of those results is sent through an activation function as an input. The activation function used here is a hyperbolic tangent, which scales it from -1 to 1. And then that is the output that is sent out of a node. The one caveat is that in the output layer, the final layer, a different activation function is used. Instead of hyperbolic tangent, it's linear, and this allows it to have a much larger range of values to output. Performance is quantified as a confidence level prediction interval around a bias value, using this equation here. We have the bias, which subtracts the predicted value, or the actual value from the predicted value, and then multiplies it by the amount of predictions made. This will trend towards 0 as more predictions are made, but that should make sense. Hopefully, your model will not have an inherent bias, and if it does, then as the predictions increase, then that bias will show itself. The prediction interval is, in this case, what is more telling as to the performance. It is a root mean square error, and this quantifies the amount of variance in the results and how likely it is that you're going to be within a reasonable distance from a good result. That goodness is quantified with a z-score from a standard Gaussian distribution, which is then multiplied by the output of the rest of the prediction interval equation. And then that is basically error bars around any prediction that is made. So for thin lines, we take the lowest average row height and extract that to get our truth value. From the depth map, we find the line and calculate the mean depth of it. This line is found as a depth from a found surface height, which is the mode of the depth data. So the most common value, all that green in this map here, is going to be the floor value. And the depth below the floor is scanned in the x direction, so left and right along this map. And so each row of pixels left and right is averaged, and the lowest average is found as the scanned line. And in this case, the lowest average depth has 11.5 nanometers below the floor height out of the population of 46. For wide lines, surfaces are separated to compare their roughnesses. We find the dividing lines between the top surface and the line bottom surface. These are the centers of the slopes or the walls down, and so they have the greatest absolute slope. They're the steepest. We remove those and then also a section around it to try and remove as much of the wall as possible to avoid getting any of the slope in the way of the roughness data and the variance in it. So we remove by a half-wall width scalar, which is defined as 2.5 times the thin line depth. Testing different scalars for this 2.5 was found to be the most successful in separating out the two surfaces without collapsing in the middle surface, the line bottom surface, too far. You can then measure the roughness of each surface as the standard deviation of its height. The maximum measured line bottom roughness from our data set of 12 was 2 nanometers. Network configuration was optimized by testing different combinations and settings. Checked different amounts of nodes in each layer and different amounts of hidden layers going through. And the best found configuration was the one shown here, which is 6 hidden layers, each of which contains 16 nodes. I also found that it was most successful when averaged across different weight and bias initializations. So the model is initially randomized, and by switching up the randomization only 6 times, we found that it averaged out some of the error that would come from initializations. The results show successful modeling for thin line depth and somewhat successful modeling for wide line roughness. Thin lines predicted the line depth, and the mean error of the bias was negative 4.5 times 10 to the negative 4th nanometers, or negative 3.9 times 10 to the negative 3rd percent of the maximum measured depth of the data set, as you can see in the left figure here. The prediction interval with 95% confidence was only plus or minus 0.2 nanometers, or 2.1% of the maximum measured depth. As you can see in the figure, that's a very small proportion. For wide lines, predicting the line bottom roughness, the mean error, the bias, was negative 0.03 nanometers, which is still small but not quite as small, negative 1.4% of the maximum measured roughness. The prediction interval with 95% confidence is 0.7 nanometers, positive and negative, which is 35.9% of the maximum measured roughness. This can be seen in the figure on the right. Conclusion: an ultrafast laser is used to write lines in glass surfaces. Thin lines are measured as depth only, and the feed-forward neural network is able to predict the average line depth with a very small prediction interval. Wide lines are treated as 2 separate surfaces, each with a depth and a roughness. The feed-forward neural network is able to predict the average surface roughness of the line bottom with a somewhat small prediction interval. This process can be improved by using larger data sets, especially for wide lines, comparing surfaces before and after polishing, and exploring image-based deep learning methods to potentially increase accuracy. Thank you.